Hello everybody, I'm Quentin, and with Ahmed, we're going to give you a status on the GlobalISel work and what we've been up to for the past year and some present facts and our vision for the future. So let's start with what is GlobalISel. So a brief recap. So GlobalISel is this revamp of our instruction selection framework. So I won't go into the motivation and the context of why we are doing that. There are already great resources for that in the talk that we did last year and 2 years ago. And also you can find a bunch of RFCs on the LLVM dev mailing list if you're interested into the details. So you don't have to watch the video just now. I'm going to have the presentation self-contained, so don't worry. So let's look at GlobalISel overview. So GlobalISel is basically a set of machine function passes that work together to lower LLVM IR from the left to machine inster to the right. In the middle, the different passes use this generic machine inster representation, which is not a new representation, it's just machine inster representation with additional opcodes and some types on the virtual registers. And that's about it. So let's now go through what we've been up to for the past year. And we start with the generic machine inster. And in particular, we made the type system more concise. Let's see how it works with pointer displacement. So before I go into the details of the example, let's describe briefly the representation here. So as you would expect, you have different instructions and things on the right-hand side of the assignment operator are arguments, and things on the left are definitions. So one thing that's special here is this guy. So the percent number are the virtual registers. Then they have this underbar here, which is just a placeholder for the register class of the virtual register or the register bank. So at this point, that means that this virtual register is not assigned to something that we know. Finally, the special thing is the type. So here we have a pointer on address space 0. So P means pointer and 0 means address space 0. And you have other types in this example like S64, which means scalar of 64-bit, which is with a size of 64-bit. And you have S32, which are scalar of size 32-bit. It's pretty straightforward. So let's go back to the example and focus on this pointer displacement. So previously, when you wanted to do address calculation at the machine inster level, you had to do this pointer to int translation to make the type system happy, and then you can do the operation on the integer and then move back to the pointer to use this pointer. So we didn't like this gymnastics, so we make it easier, and instead we have this G underbar GEP, where you can directly do the computation on the pointer type. Next is pointer alignment. So when you allocate some things on the stack or just allocate pointers and whatever, you may want to align the pointers to some boundary. And to do that, you have to mask some bits out of the pointer. So to do that, you have to create a constant for the mask, do the same gymnastic of making the pointer type back to the integer type, and do the masking and back again. So now you can do that with just one instruction, which is this G underbar PTR underbar mask, which take the pointer as argument and the number of bits you want to strip out, the low-level bits you want to strip out from the pointer. So if you compare what we have previously on the left to what we have now, it's much more concise. So one thing to keep in mind is that GlobalISel is a work in progress. We don't know if it's a good idea to have pointer types at all in the generic representation, but at least it's easier to deal with them now. So next, what we added is a fallback mechanism to selection DAC to make the bring up easier. So why is that? Let me explain that a little bit. So let's say you have this compilation unit with a bunch of functions. GlobalISel may be able to select the first function, and some other, but at some point, maybe it doesn't support one function and it will fail. At this point, the whole compilation unit will fail, and you cannot check that what you were already able to select is correct. So that's sad, because that means that if you want to check something, you have to support all the thing to be able to run it. So instead, we added a fallback mechanism where you can just use the legacy selection DAG instruction selector to select this specific function and then move to the next one. So you enable this thing by using this command line option, which is GlobalISel abort equals 0 or GlobalISel abort equal 2. The difference between those two is that 1, so the equal 2, is going to print warnings when this fallback pass is triggered. So that helps you identify where GlobalISel is not supporting something and give you a hint of where you need to look at. So to support this mechanism, we had to make some changes to the pipeline. And in particular, we added 2 passes. So as you would expect, we have to use selection DAG to do the actual instruction selection if we need to. But we also have this reset machine function pass that is going to do some work for us. So let me describe that. So let's say we have this function I that we said is going to fail. So the IR translator does some stuff about it. It may work. Then it moves to the next pass. It does some stuff. It may work. Then move to another pass, and maybe it fails. So at this point, the pass that failed is going to annotate the function using the machine function properties that already exist in LLVM to say that, okay, this function failed for ISL. So when you do this kind of marking, all the subsequent passes are going to just skip the function and do nothing until you reach the point of this reset machine function pass that will look at this property, and if it's set, is going to clean up the function state and hand it over to selection DAG. And then selection DAG can do its work, and you can move on to the next function. So that was the change that we made that affect all the passes. So now let's dive into each passes individually. And we start with the IR translator. So the IR translator is kind of a boring pass because it's just a mapping from LLVM IR to generic machine inster. And really what you need to know about this pass for the pass here is we made some change to the call lowering API, so which is responsible for ABI lowering. And we supported more instruction like intrinsic and these kind of things. And that's it for the IR translator. So next, we move to the Legalizer. So more interesting things happened on the Legalizer. So let me dive into it. So first, let's introduce what is the purpose of the Legalizer. And I'll do that with an example. So we don't have a concept of as illegal type in GlobalISel. Instead, something is legal as long as you are able to select it. So for the purpose of this talk, so let's say we are looking at this bitwise operation, or for a ACE128 type on a 64-bit target. So that means your register file is not large enough to deal with that type. So you have to do something. So in particular, what you want to do in that case is you want to split this operation into 2 chunks of 64-bit values. When you do that, you will notice that on the definition of the VREG 6 has 2 definitions now, the low part and the high part. The problem with that is that it's not in SSA form anymore. And at the early stage of the machine inster, we are supposed to keep SSA representation. So actually what you need to do at this point is to introduce temporary definition that you stitch back together to produce a big value. And that's the purpose of this G-sequence instruction. Likewise, you don't want to have magic things happening on your input parameters, so you make the changes explicit with some G-extract that are going to extract the bits you want in the right values. So the one thing to take away from that is that you end up with a bunch of instructions that are here to make sure the type system is consistent. And we call those things the legalization artifacts. So why am I talking about those things? So the reason is because we made the semantic simpler on those instructions. So let's look at this G sequence, for instance. So in that case, it takes 2 arguments, but really it could take an arbitrary number of arguments. And in particular, in this example, they have the same types, but really they could be anything. So that means that for the legalizer, it's actually very difficult to reason about this instruction and to do the right thing. It has to do crazy bit shifting and masking and whatnot to do the right thing for your target. So instead, we introduce a new node that we call gmerge_value. It has a much narrower semantic, and in particular, all the input have the same type. So now you're dealing with something that is much more regular, and it's much easier for the generic code to do the right thing. So likewise, the gextract has the same kind of craziness. The output here in that example has the same type, but really there's nothing preventing you to do whatever you want with the types. So to avoid, again, this craziness with bit masking and whatnot, we have a new node that we call GUnmergeValue, and we enforce that we have the same type. So let's wrap this up. So first, G sequences are gone. You can't use it anymore. So if you want to have something that is kind of a G sequence, you'll have to make a sequence of instructions to build this sequence. And we actually have APIs for that. Second, the gextract still exists, but only have one result. The reason is because they are still used for extract values and this kind of things that deals with structures from the LLVM IR. And finally, for all the other use cases, you will use these gmerge and unmerge value instructions. All right, so now we know the fundamentals about the legalizer. Let's dive into the algorithm. How does it work? So last year, we introduced in the legalizer info this setAction API that basically you tell the generic framework for a given operation and a given type what action you want to happen on this generic instruction. You will notice this op-index argument in here, which is just here to specify which type you're talking about for instructions that have several types, like ICMPs, where you have the Boolean type as a result, and the input type as integer. So you want to differentiate the action based on the different types you may have. The tutorial tomorrow will go into more details on that. So as action, you have a bunch of them. In particular, you can say that something is legal. Also, you want to say that you have to narrow a scala. So what this action does is taking a type, the input type, and divide it by 2 and splitting things by 2. Likewise, you have the widen scala that is going to multiply the size type by 2. And you have a bunch of other actions that are all well documented in the header. So let's see on an example, how does this work? So let's say you have this S16-bit unsigned remainder, so urem, and you have this action that says, oh, I want to widen the scala for this operation. So that means you're going to multiply by 2 the size. So you do that, you end up with a unsigned reminder of size 32-bit, and you have a bunch of legalization artifacts like zero extract and truncate to make the type system coherent. So last year, you would end up in this situation where now you have a urem of size 32-bit, and the legalization algorithm would stop. So that means that if that thing was not legal for your targets, GlobalISel would have failed. So now, thanks to Christophe Bale's work, we have a legalization step going on, and that is going to keep looking into the table for set actions, and is going to see that, oh, actually this urem needs to be lowered in a simpler sequence of instruction. So it will do that, and then it would go bottom up, look at all the instructions that you created, and look at the set action for those things. So here, the sub is legal, so there's nothing to do. The multiply is legal, there's nothing to do. And finally, we look at the division, and it says it's a lib call, and it's going to expand it, and the legalization is done for this sequence. So that means that for you, when you're using the Legalizer framework, there's actually nothing to do to use this new legalization step algorithm. The one thing you need to be aware, though, is that there's no checks that your set actions don't create a cycle. So let's say you want to narrow scalar to some type that actually gets widened in some other case, then you have a cycle into your actions and you will end up in an endless loop. And it's not something we detect right now. So just look out for that. So that was the Legalizer. So let's move to the reg-bank select. So what changed on that path? Not a whole lot, actually. So mainly what we did for the past year is that we added a partial table gen support. So that means that now instead of describing your register bank in C++ code, you can write this target description file. And also we moved away from dynamically allocated structure like small vectors into statically allocated structures like arrays. So that means that everything is pathed to use table gen, but we don't quite generate it yet. So next is instruction select. So we spent a lot of effort on that part, and in particular, we worked on the table gen support. So what does this mean? So in most target on LLVM, if not all, you have a target description file that is written for selection DAG and express how you're going to take some patterns and map that to target-specific instructions. And we want to reuse that as much as possible because we don't want you to have to start from scratch when you port to GlobalISel. So let's look at how TableGen works right now. So on the left, it's taking this selection DAG target description. It feeds that into a CodeGen DAG patterns, but it's going to do for you the pattern fragment expansion, but also do the generate the additional patterns for commutative operations and all this kind of interesting things. Then it feeds that into the DAG-ASL emitter that is going to generate some C++ code for selection DAG, sorry. So for GlobalISel, we plugged in just after this CodeGen DAG patterns because we want to reuse all this nice logic about commutativity and whatnot. So we have this GlobalISel emitter that is going to generate some C++ code and some state for the GlobalISel state machine used in the instruction selector. So let's look how it works on an example. So let's say you have this pattern that has been extracting from AR64, which is how you select an add with an immediate on this target. So one difficulty here is that if you look at this pattern, we have this add here. So one problem with this add is that this is actually a selection DAG node. It's not a generic machine inster. So there, you need a way to map this selection DAG node to some generic code. And we do that with what we call the selection DAG compatibility layer. And it's all in this selection DAG compat.td file. And you will find these definitions about GI node equivalent, where you say that this add is equivalent to this GAdd. And that's how you tie things together. So next in this pattern, you have this type, which is quite of an interesting guy. Let's look into it. So this thing is actually the worst thing you can imagine for GlobalISel. This is a complex pattern. So what does this mean? It means it references some C++ code that has been written for selection DAG. So there's no way we're going to be able to use that. So still, we'll have to do something about it. So what we do is that in the target description, you had a new definition that is going to explain how you're going to map this complex pattern to a complex pattern for GlobalISel. So you do that with this GI complex pattern matcher, where you describe the name of the C++ function that is going to do that. And then you tie things together with this complex pattern equiv node that is going to tie things together with the existing selection DAG node, so that when the compatibility layer is going to generate the C++ code for you, it's going to know how things map together. So now if you look at the C++ code that is the prototype for those methods, for selection DAG, you have one input SD value node and a bunch of other parameters that are actually the result of the function. So for GlobalISel, you have a little bit different prototype. So you take a machine operand as input, which is your equivalent of selection DAG value. But instead of changing some values in the prototype, you actually return a renderer function that is going to be covered during the tutorial. But basically, this is a Lambda function that worked on the MI builder, and you tell it how you're going to happen your instruction to the currently built instructions. So, okay, we have everything we need to be able to support this pattern in GlobalISel. So what do we do about it? So the GlobalISel emitter is going to generate this big table for you, and I'm going to get through some high-level principles so that you know how to read that. So first, each pattern is encompassed in what we call a try block. That block basically means that anything that is going to be try in that block, if it fails, it's go back to the scope and jump to the label that is listed here. The other high-level things to see is that you have this GIM nodes or opcodes that stands for GlobalISel matcher. So first you do the checks, and then you move to the GIR, which are the GlobalISel renderer. So that's when you modify the representation. So first you do your checks, then you do the modification. There's nothing interleave. You have to do things in a consistent order because we don't try to clean up things that you try. So if you start to render things in the middle of some checks, then there's nothing that's going to clean up after you, whereas selection DAG would have done that for you. So now if you look at specifics, it's pretty easy to read. So here we have a node that checks on the number of operand. You see the number of operands that is listed here. It matches the pattern. You have 3 operands. It matches the 3 operands you have in the pattern. Then you will see the complex pattern that you would expect for the type we mentioned previously with the name that we described to do the binding between selection DAG and GlobalISel. And also you have your complex renderer that is going to be called at some point. So that's all you need to understand with GlobalISel tables. So one thing that may help as well if you have to deal with those tables is to use the -debug output from the instruction selector pass. And with that, I'll let Ahmed talk about present facts.
All right. So let's talk about the current status of GlobalISel. So the most important thing that changed since last year is that currently we're not an optional framework anymore, so we're built by default as part of any LLVM build. So that means that we can clean up a lot of the things that we had to do in order to be optional. So last year, for instance, we talked about the GISel accessor and a bunch of target pass config hackery that you don't need to do anymore because now everyone gets GlobalISel, whether you want it or not. So we started working on lots of targets. So of all the many targets that we have in tree nowadays, there are at least 4 where we actually have some level of support in GlobalISel. So we started working on those, and other folks in the community also did. But the one that we've been focusing on ourselves is mainly ARM64. So that's the one that we use for the prototyping new features and all. And there's also other out-of-tree backends. So you'll hear about a couple in the next 2 days that also use GlobalISel. So let's go back to ARM64. So our goal for this year was to replace ARM64 or 0. So let's see how that goes. So if we see the test suite and specs, so all the things that we measure on a regular basis, we actually can cover most of it without ever falling back to selection DAG. So as Quentin mentioned, we fall back when we don't support, and we're down to less than 1%, a fraction of 1% for the test suite. And the same for Clang self-host. So also we're like somewhere around 3 to 4%, but that's because Clang self-host has a little more first-class aggregates, C++, that means that some things that we can't really support right now in GlobalISel. And finally, all of our internal software, we're also really close to 99%, where we support all of this with just straight GlobalISel. So now if we talk about table gen, so Quentin mentioned that we have the selection support for the GlobalISel emitter. And so for ARM64, we can support about a third of all the existing patterns. And that's because a lot of the remaining ones there's a very long tail of special vector, neon, intrinsics, and all that. And those are the ones that we don't really support right now because we haven't done a lot of work on vectors. So ARM, it's the same. There's a little less of these intrinsics, so we have a little better support. But x86 is really special because it turns out there's over half of all x86 patterns are just some kind of vselect for AVX512. And that's just beautiful. So we don't support any of that, and we don't support any of the other beautiful parts of AVX, AVX2, AVX512, all that stuff. So we have very, very little support in x86. But we're getting there. Lots of vectors, make progress. But now let's talk about the most important aspect of all this, which is the actual performance. So we went and we measured lots of things. So starting with code size. So code size is not great, but not too bad. So we're like somewhere between 10 to 20% bigger on average. And there are a few very obvious low-hanging fruits that cause us to be there. So for instance, one thing that we do right now is we don't try to fold immediates very well. We don't try, and that causes us to have lots of rematerialized constants where we don't need to. And so if we compare that to FastISel, it's not ideal, but there's lots of things we can do. So for instance, for the constants, one big problem that comes from not trying to fold the constants is that we end up with this kind of pattern. So for instance, here we have two blocks that use the same constant, and we always emit the G constant, so that's the instruction that materializes the constant in the VREG. We always emit that in the entry block. And with the fast register allocator, you end up with spills, and you end up trying to reload the constant every time you use it, which is obviously terrible. So for now, to work around the simplicity of the fast register allocator, we ended up changing the way we emit constants so that we relocalize them to always at the first point of use, which makes it much better for this kind of thing, but it's something that is really working around the fast register allocator, so something we want to improve in the future. And so with that, we go from numbers around 20% to something a little better, so we gained a few percent. So we're somewhere around 10 to 15%, and our original goal was somewhere around 10%, so it's not too bad. So now if we talk about compile time, which is the one that actually matters at O0, so they were actually really good. So if we compare to FastISel, so this is the overall compile time, so the entire compiler, including the front end and all, we're actually somewhere below 5% to above 5 to 10%, which is exactly our goal. So our original goal was no worse than 10% in the first iteration. And especially if you compare it with selection DAG, so if you just disable FastISel at O0, that's way worse. So that's freebies, way better than selection DAG, obviously. But now if we look at the compile time for each of the individual passes, so as Quentin mentioned, we have 4 passes, 4+1. We are actually pretty good. So again, if we compare with FastISel, one interesting observation is that we spend less time in all of our passes than FastISel does all of FastISel. And that's because FastISel has lots of fallbacks. So the main advantage of GlobalISel is that since we can do all the legalization ourselves, we don't have to fall back to selection DAG as often. But we still have to do that sometimes. So when we do a fallback, we end up falling up on the whole function, like Quentin explained. And that has huge cost because we end up trying to go to FastISel, and FastISel inevitably doesn't support it either. So we go to selection DAG as well. So that's something that, even though we have 99%, we really want to get to 100% so that we don't ever fall back to selection DAG. But now if we look at these passes normalized only GlobalISel, it's interesting data. So for instance, IR translator, which is the pass that does the initial building of MI, is the one, it's a pretty expensive pass. And some of the others are also pretty expensive. So instruction select, for instance, since we added a lot of table gen, so now there are lots of things that we can improve in the table gen lowering. So for instance, right now we don't try very hard to reuse existing instructions, so we end up rebuilding them a lot of time. And we also emit a state machine that's not as optimized as it could be. So we have lots of ideas on how to improve this. And we think the ISAL, the instruction select pass time is going to go down a lot. And you can see that's the same in the other passes. So for instance, the Legalizer is something that we worked a lot on improving, even as recently as the past week. And we still have regbank select, which is something that doesn't have lots of effects on O0, so it's mostly necessary for the consistency of the MI. But it's still something that's pretty expensive. And that's something that, as Quentin explained, we switched to using statically defined mappings for each operand to a regbank. And we think there's still lots of room to go forward there. So for instance, we write a lot of these by hand, and we also have some dynamic component to map them to instructions. And we think that we can generate a lot of that with TableGen and stop paying this cost for regbank select at O0. And so now runtime is the last aspect of performance. And there it's pretty much what we expected, so somewhere between 20 to 30% worse. And it carries forward in the rest of the test suite. So it's pretty much what we expected, but it's not really something that lots of people care about for O0. So now, how do we go forward from here? So we think that the numbers right now are good enough that we can consider switching the default for ARM64 0. So ARM64 because it's the one where we actually have the most support right now. But beyond that, there are lots of things that we need to do. So for moving beyond O0, we want to flesh out the rest of the pass pipeline. So right now, we only ever use a fixed pipeline of these 5 passes. And we could reuse some of the existing ones and add others. So for instance, machine CSC is the obvious one. We also want to kill the localizer. So as we explained, that's really working around deficiencies of the fast register allocator. So Matthias had some ideas for improving the register allocator, but we also think that maybe there's some chances for improving the greedy register allocator so that it's not as expensive, so that somehow we can move forward and stop generating bad spills at O0. And finally, CodeGen Prepare is also something that has always existed only to work around deficiencies of selection DAG. So since now we actually have the whole function alive at the same time, so we can actually start doing more of the optimization that CodeGen Prepare does, so like moving things next to their uses. We don't even need to do that most of the time, so there's lots of things that we can do without ever having to need something like CodeGen Prepare. So now, beyond O0, there's more that we need to do. So for the selection DAG compatibility layer that Quentin mentioned, we can use that to do a lot more. So for instance, right now we only use it to emit ISAL, but we can also use it to emit legality info. So as Quentin mentioned, we have this whole set action machinery, and we can deduce that just from looking at the patterns. So for instance, in this case, we have a pattern for a mol I32, and we know that we can just generate set action for that because that's what being legal means that we can select it. And the same for register bank mapping. So we started generating the register bank definitions, but we can also generate the individual mappings for each of the instructions and the operands inside the instructions using selection DAG, because again, we know that for this small I32, then we can go to the GPR register bank. And finally, as we move away from selection DAG, we'll have to consider writing our own selection patterns. So pure GlobalISel patterns, which would still reuse lots of the machinery that we have in TableGen, but would look pretty different. And so before we get there, there are still lots of things we need to do to get rid of selection DAG. So we still need to have 100% feature parity. So for vectors, are the biggest problem right now. So we have some outstanding patches to add some initial support, but there's lots of work there. So improved performance. So as we explained, we have lots of ideas on how to improve the performance of the passes and the runtime performance of the generated code. And finally, of course, tested way more. So we tested it on everything that we could get our hands on, but you guys have even more interesting code out there. And so one thing in particular that we want to call out is combines. So if you think about combines, it's really the same as this. So this is some ISAL pattern from ARM64 backend for a special kind of FMA. And in both cases, it's really the same. It's just a transformation from one instruction or set of instructions to another. So in this case, we could imagine representing combines as another special kind of pattern in TableGen that expresses the input state and the output. And that's something that, again, we could repurpose the existing TableGen backend to emit at least some of enscombine, and then the GlobalISel combiner, which we'll need eventually. And finally, we can go even further and add some hooks. So for instance, one ability that decombine has that we wouldn't have in this case is the ability to say whether a combine is desirable at any given time, any given point in the pipeline. So for instance, there are some things that you only want to do before legalizing. And this is something that we need to express. So that's other things that we need to consider. But before we get there, lots of things we can do to improve the tools. So this year we improved the mirror test format a lot, but we still think there's lots of things to be done there. So go watch the tutorial and you'll see there are other improvements there. We also made improvements in the MI API. So now we have MI builder so that you don't actually have to go and mess with all the registers and all the build MI manually. So it's a much easier experience. And we also have, so some things you could do is generate some of the regression tests. So we generate all the instruction code from the selection DAG patterns, but you could also generate at the same time the regression tests, at least for the ISEL parts. Because that's a common problem, which is that someone changed TableGen in a way that is not visible to all the tests, and you can't just expect people to cover everything in the test. And finally, something that's way out there is some kind of migrator from SD node codes, all the DAG get node and all that, and all the definitions of ISD app codes and all, to something that's closer to GMI. So that's something that some very brave soul could try doing with ClankTidy, but that's a problem for another day. But until then, we need lots of help, so all the contributions are welcome, so you can do patches, you can do reviews, you can try it on your backend, file reports, and we're always very grateful for all of that. Thank you.
Thank you. And we have time for a couple of questions. So, no questions?
Thanks. So one of the features I noticed that's missing from GlobalISel that Selection DAG has is the ability to insert custom target-specific nodes during the legalization step. And I've tried this in the past and had a little bit of trouble having it interact nicely with the register bank select. So just was curious if that was the kind of thing you were planning to support, or if there's some sort of other way that we should be looking at implementing that.
So the tutorial is going to cover a little bit of that. Right now, we don't have any plan to give a generic support for these kind of things. But if there's more user of that, maybe we should think about it. And if you want to contribute on that, yeah, by all means.
Okay, thanks.
But to be clear, it's something that you can do. I think there's, yeah, we might need some help in register bank select, but it's not, there's no like actual obstacle right now, right?
No, but yeah.
Yeah, I think the problem I was having was I wanted to be able to use register bank select on the custom nodes, and it was requiring me to add a specific register class when I created those.
So I guess one problem could be that it's in the wrong namespace of opcodes. It's, well, we can talk about it.
Yeah. It's not directly to this.
Okay, any more questions?
I have to ask, how good is GlobalISel at handling debug info compared to Selection DAG?
So we use the LLDB test suite, I believe. And I think Tim would know for sure, but I think we were on par with Selection DAG. That doesn't mean we are great, but at least it's not uncovered by the test suite. So yeah, if you have specific tests that you want us to run or you want to run, that would be great.
Okay, more questions? No? Then, thank you, Quentin and Ahmed.
Thank you.
Okay.